In this video, we'll continue to learn about addition reactions to alkenes. So last time we talked about adding halogens, halohydrins, making alkanes, and cyclopropanes. This time, we're going to focus on forming alcohols. So we're going to focus on forming our alcohols here. When we form an alcohol, what we're doing is adding the equivalent of a water molecule to our compound. So the simplest way to form the alcohol is by adding water. Literally just add water to your alkene. And then you also need an acid catalyst. And the catalyst is quite often shown over the arrow. And that's because in the course of the mechanism, the catalyst gets regenerated. So that's why we consider it more of a catalyst and not a reagent or a reactant. But if you take your alkene, add your water, throw in a little acid catalyst, you get an alcohol. Now the acid catalyst, it depends how much you add. If you add too much and you have a concentrated acid, that can actually cause the reverse reaction to occur. So if we want to go from our alkene to our alcohol, we need to use dilute acid and have more water around. If we want to go from our alcohol to our alkene, then we need a concentrated acid and less water around. So in the course of doing these reactions, remember the acid we're using is a dilute acid. We don't want to use concentrated acid. If you do use concentrated acid, then it goes backwards and it goes from the alcohol to the alkene. So now let's look at the mechanism for our hydrations. So first we start with our alkene and we're in a solution of acid. So if we write our sulfuric acid as such, the first step that will occur is the alkene will come and grab a hydrogen from the sulfuric acid. And if we remember the orientation of this, that carbocation that we're going to form always goes on the less substituted side. So your hydrogen that you added goes on the more substituted side. And then our next step, we're going to have our water molecule will come and attack that carbocation, which gives us our product here where we have that water attached to it. Now you see that oxygen has a positive charge. We need to remove that positive charge from the oxygen. And so now here, our conjugate base from that acid catalyst that we started with, it can come and grab a hydrogen and move electrons back down to the oxygen. This will allow us to form our alcohol, and then we've also regenerated our catalyst in the course of that reaction. A couple things to note. Your carbocation forms on the more substituted carbon. So we're going to follow that Markovnikov orientation here. So this means our hydration regioselective. It follows the Markovnikov rules. And since we form this carbocation intermediate, here, we could potentially get rearrangements. So our hydration may take place with rearrangement. And so a couple issues that occur with this is the alkene is typically not soluble in water or the acid. And since your alkene isn't soluble, it's kind of hard to do this reaction. You also tend to get rearrangements, and the equilibrium actually favors the alkene. So we'll call our issues. So the alkene is insoluble in our solvent. We get our rearrangements, which means we can end up with more than one product. And then the equilibrium usually favors the alkene, not the alcohol. So we're not going to get as much of that product as we want. So now what if we don't want a mixture of alcohols? What if we want a higher yield? We need to find a better way than just adding water and acid. So we have a couple different ways. One of those is oxymercuration, demercuration. So an oxymercuration, demercuration, complicated name, but it's okay. What it does is it eliminates the rearrangements that can occur during our addition of water. And it's a synthetic way of making a Markovnikov hydration, but it's still somewhat limited. And so it's our alternative process to just adding water and acid. And it can yield a Markovnikov product without the possibility of rearrangement. So we eliminate the rearrangement, we can create a higher yield for our product. And so what you do is it happens in a couple steps. You start with your alkene, you do your oxymercuration where you add your hydroxy group and you also add a mercury group. Then you eliminate off the mercury group. You do a demercuration and you end up with just your alcohol product. So when we write out this reaction, it actually gets written out in two steps since we have two things occurring. Step one, we have our mercury acetate and water. And then step two, that demercuration, we use sodium borohydride to remove the mercury group. And that yields us our water. Let's look at the mechanism now. So let's say we have our alkene here. The first step in that reaction is we're going to add the mercury group. So one of the acetate groups has come off, which means our mercury has a slight positive charge to it, but it still has a lone pair. So the alkene is going to attack that positive charge, and that lone pair is going to attack the less substituted side. And because the less substituted side is less hindered. And so then the mercury lone pair is going to come and attack the carbocation that's forming. And what that does is it creates a three-membered ring with the mercury. And this is what we call our mercurium ion. Then what's going to happen is our water molecule is going to go and attack the more substituted side of the mercurium ion. When that happens, the electrons from the bond here move up onto the mercury. So now we can see we have our mercury on one side and our alcohol is on the more substituted side. And this results in our organomercurial alcohol. So then the next step is the sodium borohydride comes and reacts with the mercury by adding a hydride ion. So our sodium borohydride, when we look at that, that's a boron with 4 hydrogens. It's a negative charge, and our sodium is our counter ion. So what the sodium borohydride is, it's really an equivalent of a hydride ion or an H minus. So this hydride ion goes and takes the place of the mercury. And when that happens, we end up with just a hydrogen in its spot. And then your sodium borohydride changes. Then your sodium borohydride converts to a different product. You end up with mercury solid and acetate. So one thing to note about the mercurium ion, this mercury here pulls a lot of electron density towards it. So these carbons that it's attached to, they have a considerable amount of positive charge on them. That's why the water molecule can go and attack it so easily. And so this will give us our Markovnikov product. So we have Markovnikov orientation, where the hydroxyl group of the alcohol is on the more substituted carbon. One setback about doing oxymercuration, demercuration is we are using mercury. We have to use mercury in this reaction, and mercury is highly toxic. So one drawback for doing this is you're doing something with a highly toxic compound. But it does give a better yield. So you have to think about what trade-off you would want. One slight variation on the oxymercuration demercuration is called the alkoxymercuration demercuration. And this is where instead of water, we have an alcohol. And so your alcohol will serve as a solvent in this case. So it goes through the exact same steps where we have our mercury. And now instead of water, we can do something like methanol or ethanol or propanol. And then our second step is still that sodium borohydride. Now, instead of giving an alcohol, it converts it into an ether. So this is one way to get ethers with a Markovnikov orientation. And so one last thing, you can see the alkyl group and the oxygen here now end up on what was our alkene. And so what if we don't want the Markovnikov orientation? What if we want it opposite? What if we want the anti-Markovnikov orientation? For that one, we can use our hydroboration oxidation reaction. So this one is still a two-step process where we have our boron in THF, and then the second step, we have hydrogen peroxide and sodium hydroxide. So what happens here is this gives our anti-Markovnikov addition, or we can think gives our syn stereochemistry. And then you can also use, instead of the BH3, you can use diborane. which is B2H6. So now looking at the mechanism and looking at how this actually occurs, it's not a very straightforward mechanism. It goes through a lot of steps. So what'll happen first is your alkene will react with your borane. And so what they'll do is they'll coordinate where the alkene will bond to the boron and the hydrogen will move over to the other carbon. So now your boron, you can see, is on the less substituted side. This is because boron is bigger than the hydrogen. And so this is going to repeat with that same alkyl group each time. So each one of these R groups here is this alkene. So if you were to draw it out, you have boron with its 3 groups attached to it. And so you can see with this trialkyl borane, it's incredibly bulky. Since it has those 3 different alkyl groups, it gets really, really bulky. It also means you need 3 equivalents of your alkene for each boron. I also want to point out that the boron and the hydrogen, they add to the same side of the molecule. So this is a syn addition. And the next step in the mechanism is the oxidation. We got to do that step 2. So here's where we have our hydrogen peroxide and our base. And so the hydrogen peroxide and base will react to form our hydroperoxide. And this then goes and attacks the boron of our trialkyl borane that we just made. So when our oxygen here attacks the boron, now our boron has a negative charge. And what's going to happen is one of the R groups is going to migrate to the oxygen here and kick out the last one. So it's going to do a rearrangement, and your alkyl group goes from being attached to the boron to now it's attached to the oxygen. So if we think about that trialkyl borane that we drew on the other page, you'll have your group here, and then you'll have your peroxide. And then you'll have your peroxide will come and attack that boron to give us this compound here. And so what will happen is that entire alkyl group will rearrange onto the oxygen. So our entire group here moves to the oxygen, which then causes this one to get kicked out, and we lose a hydroxy group. So that's how we end up with our product down here. And then after that happens, and it repeats itself several times, so now we have these oxygens attached to those different alkyl groups and a OH attached to the boron. Oops. So then after that happens, when we start here, it'll repeat itself 2 more times till we have all of the oxygens with the alkyl groups on instead of the boron. So now basically the oxygens have inserted themselves in between the boron and the different alkyl groups. When that happens, a hydroxy will come and attack the boron to create our product here. The boron will then go and lose one of the OR groups. one of the alkoxide groups. When it loses an alkoxide group, now that's floating in solution, and that gets protonated by some of the water that's around, which gives us our final alcohol. And this step here will repeat itself with the other OR groups till we end up with all of the product converted to alcohol. And your alcohol here it's our alcohol group here. We'll now have that OH on the less substituted carbon. So this is how we get our anti-Markovnikov orientation. And so one thing to note with this reaction, it is a stereospecific reaction. What this means is when we have different stereoisomer of our starting material, that'll give us a different stereoisomer of our product. And so now you've seen 3 ways to form alcohols. So now we've looked at forming halides, dihalides, halohydrons, alcohols, alkenes, and cyclopropanes. In our last video on this, we're going to look at forming 1,2-diols, carbonyl compounds, and epoxides.